Hi everyone, welcome to part 2 of the Wurlitzer 532 tube amplifier testing and troubleshooting. In part 1, we focused on testing the input power transformers that make up the power supply for the amplifier, and I will include a link to that video in the description because it talks about some of the safety tips to keep in mind when working with these amps and the high voltages especially that we're working with. In this video, we're going to be testing some of the key points in the signal amplification circuit and injecting a test signal so that we can follow it along the signal path and make sure it's getting amplified properly from the input all the way through to the speaker outputs. In order to trace a signal through our amplifier circuit, we first need to understand the basics of how amplifier vacuum tubes work. So I drew this diagram of a triode vacuum tube that was invented by Lee DeForest, and triode simply means a total of 3 inputs or outputs. There are also tetrodes and pentodes, but they all kind of operate in a similar fashion. In this example, we have a heater element right here, and that's heated with 6.3 volts AC. So this might be an example of like a 6L6, and the first 6 indicates the heater voltage. In the case of a 12AX7, there are 2 of these heater filaments for a total of 12 volts AC in. So the job of this heater is to basically heat this cathode here so that it emits electrons, kind of like popcorn. And at the opposite end, we have a very high positive DC voltage, usually around 200 to 300 volts, and that's going to pull and attract those electrons, creating a current. In the middle, we have what's called a grid, and that controls the current flow and acts as like a valve, letting more or less current flow based on the AC signal that's coming in. So the result is an amplified signal on the plate in the pattern of the AC input signal on the grid. And because both AC and DC can exist on the same wire at the same time, we need to put this through a coupling capacitor. And that is basically just to block the DC voltage from going on to the next amplification stage. And if we were to let the DC voltage through, we'd basically fry the grid on the next tube. And note that there are usually multiple tubes required in an amplifier, since each tube can only have the ability to amplify the signal about 30 to 60 times. And a phonograph signal that's coming in might be only a few millivolts or less, right? So, and we need to get that signal up to about 100 volts on our output transformer in order to drive the speaker. So attached to this cathode and anode here, we usually see a resistor or a set of resistors, and those are used to bias the tube. And bias simply means just setting the parameters or the configuration to make the tube operate as per its specification. So for example, let's say we have B plus here and it's 350 volts, but the tube's only designed for 250 volts. So this plate load resistor will drop the voltage to get it in the correct operating range. On the cathode side, the cathode bias resistor here is going to provide a voltage gain since it's connected to ground. And the reason it's necessary is that we need the cathode to be more positive than the grid, but still less positive than the plate. And the reason for that is if the grid was more positive than the cathode, it would actually end up attracting the electrons. And we want the anode, or the plate, to be attracting those electrons. So let's just talk quickly about how this coupling capacitor works. So thanks to James Maxwell and Oliver Heaviside, we know that the formula for capacitor impedance is the following. And because DC is a constant voltage, it has no oscillations or frequency, anything that's close to 0 here on the bottom is going to be close to infinity over here on the impedance side. So 1 divided by something close to 0 here, infinity. So the impedance is going to be very high for DC voltage. And conversely, if we have a higher frequency, 1 divided by a higher number here in the bottom is going to mean that we have a low impedance. So basically, coupling capacitors are essentially a high-pass filter. So they're only going to let the high frequency through and block anything with low frequency. So that's basically how amplification works on vacuum tubes. A couple more points I want to make. The first is that typically on a schematic, we will see these numbers around the tube, 1, 2, 4, 3, 5, and basically those just represent the pin numbers for that input or output. And those can be found by looking up the data sheets for the specific tube. The second thing I want to point out is how the signal changes as it travels through the triode. So if we were to drive the grid with a signal here, the signal at the plate is actually inverted and it's 180 degrees out of phase, while the signal that comes out of the cathode here is actually in the same phase as the input signal with unity gain. So it's actually, there's no gain coming out of the cathode, same phase. We're going to get gain coming out of the plate, but it will be 100 degrees out of phase. Now this is important when we talk about the 12AX7 phase inverter that's used in the 532, and I'm going to show you an example of what's happening there when we do the phase inversion. And the other thing that I should mention is that you can actually drive the cathode with a signal, and if the signal is actually driven from the cathode instead of the grid, it will come out of the plate in the same phase that it's passed in. So there will be no phase inversion when you drive it that way. But I don't think we have any examples of that in the 532 amp that we're dealing with here. So with all that knowledge, let's follow the signal path in the schematic so that we can come up with a testing strategy. After analyzing the circuit here, I realized that this first section here is actually demodularizing the input from the Cobra pickup and actually helping to generate the AC voltage signal. And that is really hard to simulate on the bench. And the only way that I can think of to really do that is to just inject a voltage somewhere on the circuit, not directly on the input here. And in fact, I found a note at the bottom of the schematic that said exactly that. It said apply 180 millivolt 1000 cycle signal through a 0.01 microfarad capacitor to the junction of R4, R5, C6, and C7. That is right there. So past our input stage here. So I think I have a change in plans. So I noticed that there's an auxiliary amp input right here. And if we follow that along, we go in through pin 3, which is jumper to pin 9. We go through this set of resistors and capacitors here, and then we come in through pin 11, which is jumper to pin 1. And guess what? That feeds to the grid of the 6AU6. So this makes a lot of sense and really simplifies the testing. So if I'm just focusing on the back half here with the 6AU6 voltage amplifier, the 12AX7 driver stage with the phase inversion here, and then which feeds into the 6L6 power tubes, which drives my speaker here through the power transformer. If that back half is working, then I can go back later and inject the signal in the phono preamp section here and test that later. All right, so the 6AU6 is a voltage amplifier, as you can see there, and it's going to give us our preamplification to get our signal up to line level. And as we can see from the chart here, the testing chart, if we feed the 6AU6 on pin 1 with 0.025 volts, that's 25 millivolts, on the output, we expect to see 2 volts. So that is about an 80 times gain. And so what we're going to see is our signal coming in here through pin 1, and it's going to be coming out on our plate at 2 volts. It's going to go through this coupling capacitor, and then it's going to go through a series of resistors and capacitors, and we can see that that's actually just our bass and treble filtering here. So basically we're going to get some signal shaping here based on our configuration of the tone and bass switches, and then we're going to be feeding into the grid of the 12AX7. So this 12AX7 tube here is going to give us the signal in 2 different phases, and how it does that is that half the tube is going to be giving it in one phase and the other half is going to be giving it in the other phase, and we'll walk through how that's done. So first we know that it's going to be coming in through pin 2 here and coming out the plate of pin 1, and if we look at our testing chart here, we expect to see the input voltage on pin 2 is about 0.8 volts. It came out of the 6AU6 at 2, but it went through some resistors, so we probably dropped it a bit here to 0.8, and we're going to be coming out on pin 1 at 135 volts. So that half the signal is going to be coming out through this coupling capacitor here and going off to one of the power tubes. That same signal is also going to travel down through this resistor. It's going to drop the voltage and through this coupling capacitor here into the grid of pin 7 and out the plate on pin 6 here, and then back out through this coupling capacitor here down to the other power tube. If you recall our discussion about how triodes change the phase of the signal at the plate, we can see that the signal coming into the first half of the 12AX7 is actually going to give us an inverted signal with some gain on the plate of the first side here, but that same signal is now dropped through a resistor to give it a smaller voltage, and then it's going to go into the input phase, completely out of phase with the input of the other side, and we're going to get the inverted phase on the output of the second half. So you can see here that we're actually getting phase inverted signals with equal gain coming out of each half of the 12AX7s. If we look at our testing chart here, we can actually see that the 12AX7 phase inverter input is going to be 0.8 in the first half of the tube, and we're going to get 13.5 volts out at the plate, and then that signal is fed into the next stage, but it's dropped with a resistor, and we see that we're only getting 0.26 volts in on pin 7 of the grid, but we have the exact same gain on the output of the plate of the second half of the tube. So 13.5 on both halves, and I mean that's the most important part, is that the next stage, the driver stage, we're actually giving the exact same output voltage. We can actually see that the input of the next stage is 13.2 volts. So that makes sense. There's probably some resistors in between that drop the voltage to 13.2 for the inputs of the 6L6G tubes that are the power tubes in the next stage. All right, so the next set of tubes are our power tubes, and we have a signal coming into the grid on pin 5 and an inverted signal coming into the grid of pin 5 in this tube. And we're going to come out through pin 3 here to our output power transformer, and pin 3 to our output power transformer. So this tube configuration is what's commonly referred to as push-pull mode, which basically means that each tube is only handling the positive half of the signal. So basically when the signal comes in through on this first tube here, and the output is positive, it's going to turn this tube on and basically pass the positive half of the side through. And when it's negative, it turns this tube off. And because the signal is inverted, at the exact moment that the tube is getting shut off here, this second triode is actually going to be positive. So it's actually going to turn this tube on. And the way this is accomplished is just through biasing, and the way that just the way the tube is biased. So the 6L6G only amplifies the grid voltage when it's positive relative to the cathode. So the reason why this configuration is very popular is that push-pull amplifiers generally prolong the life of the tubes. They also improve the output capacity, and they produce a lot less heat. One interesting thing I noticed here is that we have no plate resistor. So basically, we have B plus coming in here through the 5U4G. So we're getting our B plus from there. It's coming into the power transformer here on the coil. And then it's actually feeding the plate here, as well as coming through the bottom here to the plate of the other tube. So we don't have a plate load resistor. So this coil, the primary side transformer, is actually acting as a resistor as well. Plate load resistor for the two tubes. One of the things that always confused me is that if we have a signal coming in and we're only amplifying the positive half with these power tubes, how does it get merged back together properly? So as you can see here, we have the signal coming in and we're only amplifying this positive half because of the way it's biased. And again, at the plate here, it's going to be in reverse phase. So we have that part of the signal there. And then this half is going to get ignored here because of the way it's biased. And we're going to amplify this half, which again is going to get phase inverted. But here's the magic. The way that these coils are wound is actually what's going to determine how the signal comes out on our secondary side here. So what happens here is that we have the coils wound in one way, and then this side we actually have it wound in the reverse way. And so what happens is on the secondary side we get our original signal back on the output. So our signal has now made it to the output power transformer here. And the purpose of this transformer is to match the impedance of the output tubes and the speakers. So we have very high voltage on the other side here, on the primary side here. We can see that we have 145 volts in here. We definitely don't want to have 145 volts on the back of our speaker wires in case we accidentally touch that. So we want to drop down the voltage on the secondary side here to maybe from a 10-to-1 ratio. But we want to increase the current. So that's what this output transformer is going to do. It's going to reduce the voltage at the same time, increase the current on the secondary side.
One important thing to note is that the impedance on the secondary side is matched in the same ratio on the primary side. So let's say it was a 10-to-1 winding ratio here. If we were to use a 4 ohm speaker, and this was designed for an 8 ohm speaker, what that's going to do is we're going to have reduced impedance on the secondary side, which means we're going to reduce the impedance by half on the primary side. And if you can imagine, well, that we're essentially dropping the impedance that's on this high voltage B plus here that's coming in here. So we definitely burn up the we could definitely burn up the amplifier here if we use the wrong output load on the secondary side here. So it's okay to actually use a higher output load here on the higher impedance load on the secondary side. You're not going to get great performance, but at least you're not going to go and fry anything on the primary side here. Okay, so just trying to figure out how to hook up my dummy load here to make sure that I have an impedance on the secondary side to match the primary side. Otherwise, we'll have too much current on the primary side and we can blow a fuse there. So in looking at this, it looks like the speakers jack goes out to pin 6 and then it goes through the speaker network and comes in back through pin 5. But I wasn't sure about what this fader switch was doing here with A, B, C, or D. And it looks like there's an ability to hook up an auxiliary set of speakers here on this output based on the fader switch. But I was lucky enough to find the manual that helps explain it. And if the fader switch is set to phono only, all the amplifier output will be delivered to the phono speaker network and the 8 ohm line if connected. If it's set to A, then 15 watts will be delivered to the speaker network and 8 ohm line if connected, and 8 watts to the CV line. The fader switch is set to B, then 8 watts will be directed to the phono speaker network and the 8 ohm line, and 16 watts to the CV line. And if it's set to C, 3 watts to the phono speaker network and 8 ohm line, 21 to the CV line. And if it's set to D, then we have 1 watt to the speaker network and 8 ohm line if connected, and 23 to the CV line. So what that tells me is that I definitely have to have a dummy load connected to the speaker network, because all of the output will still be delivered to the speaker network and the 8 ohm line if connected. So I still need to have a dummy load connected to my speaker network here. So I'm going to hook up an 8 ohm resistor to pin 6 and 5. So here's my dummy load. I have two 8 ohm 100 watt resistors. One is plugged into the 8 ohm and ground, and the other one is actually coming through from pin 6 on the speaker output and also connected to a ground. One more thing that I just caught as I was looking at the speaker wiring is that the center tap for the 5U4G is actually coming out to pin 3 of the speaker here. But when it's not plugged in, it has to be jumpered to ground, pin 1 here. So I think that when we normally have the speakers plugged in, it actually provides that path to ground there. But because we have this on a bench, we're going to have to provide that ground center tap here. So I'm going to tie a jumper from pin 3 to pin 1. Alright, so here's the jumper wire added to make sure that we have pin 1 and 3 jumpered. So pin 3 is actually going to be your center tap, which is tied to ground, which is pin 1 there. The other thing I did in my part 1 video was jumpered pins 8 and 3 of the junction box, but I realize now that I should also be jumpering pins 5 and 1, which will, in fact, hook up this relay switch here, which will actually probably close my switch, so I can probably remove the jumper that I had in place in part 1 of my video that jumpered the switch. So I'm just going to make sure that these two are jumped here on the junction box. Alright, so I just add a couple jumper wires in this chassis plug, which is my junction box, and that is on pins 1 and 5 and 3 and 8. Before I apply a signal to the amplifier, I just wanted to do one more quick test, and that is I'm going to remove all of the tubes except for my rectifier, my 5U4G there, and I'm going to just make sure that I'm getting the correct voltages, the B plus voltages at the plates. Okay, so I have my multimeter set to DC voltage, and I have one lead connected to ground, and we'll be testing the 12AX7 first, and the 12AX7 plate is pin 1. So we are getting 390 volts there, so that looks good.
Next, I'm going to move to the 6AU6, and that is pin 5. 1, 2, 3, 4, 5 here. That's 385 volts. We're getting a B plus to that one. Now we have our second 12AX7, and that is pin 1. We're getting 386 volts there, so that looks good. Next we have our 6 and 8, which is pin 6. 1, 2, 3, 4, 5, 6. And we're getting 384 volts to that one. Looks good. And last but not least, we have our 12AU7, and it is pin 6. 3, 4, 5, 6. And we are getting 390 volts to the plate of that one. So my B pluses are all looking good. I'll also test the B plus to my power tubes, and that will be on pin 3. So we're getting 470 on the first one, and 1, 2, 3. Oh, wrong side. 470 on the other tube, so looks good. Note that we won't actually see 380 or 390 volts on the plates once we plug the tubes in, as once they complete the circuit, we'll see the proper voltage drops through the resistors on the way to the ground connection here. I'm just going to do a quick test of the heater voltages coming in here. I just want to make sure that the YY, which we had measured before, we were getting slightly over 4.7, I think it was 5, and slightly over 1.6, I think it was 1.8, so it's probably closer to 7 volts as opposed to the 6.3 that we were expecting there across YY. So I want to make sure that we're getting that 7 volts across 4 and 9 here, 4 and 3 of the 6AU6, and all the way up. I see we have some inductor here that's going to the oscillating tube, so it might be a little bit less here. But I still want to make sure that I'm getting the correct heater voltages before moving on. Okay, so I have my tubes removed and my amp is on. I'm going to be testing the 12AX7 first, and I'm looking for pins 4 and 9 and 5 and 9. So 1, 2, 3, 4 and 9, and I am getting 7 volts there, and 5 and 9, and I am getting 7 volts in this one. That looks good. Next we'll look at the 6AU6, and that's between pins 3 and 4, and we are getting 7 volts there as well. Looks good. Next we'll look at the other 12AX7, and that is also between 4 and 9, and we're getting 7 volts there, and 5 and 9, and we're getting 7 volts there. That looks good. Next is the 6A and 8, and that is 4 and 5. 1, 2, 3, 4 and 5. We're getting 7 volts on that one. Looks good. And last but not least, we have the 12AU7, and that is 4 and 9 and 5 and 9. 7 volts. 7 volts. Okay, our heater voltages all look good. Okay, so since this amplifier only has a 2-prong plug and no ground connection, it means that the chassis is going to have a floating ground. And what that means is that it's going to be subject to capacitive coupling from the power transformer, where stray voltage can appear on the chassis, usually between like 20 and 100 volts AC. And capacitive coupling occurs when AC voltage from the primary side of the power supply passes to the secondary side, even without a direct electrical connection. So basically AC voltage is leaking into the amplifier circuit, and that stray voltage will actually appear on the chassis, and it will cause it to float at about 20 to 100 volts AC. So because of that, it can be actually quite dangerous to attach this ground clip here to the chassis when it's floating, and that's because that ground clip is actually connected to the BNC connector here, which is connected to earth ground. If we look at this diagram, it'll be easier to see why this is a problem. So in this diagram, we have our breaker box, which feeds our outlet here with the hot wire, and that's going to connect to our oscilloscope, and it returns through the neutral line back to the breaker box to complete the loop. But guess what? That neutral line is actually connected to earth ground. And as you can see here, that BNC connector is also connected to earth ground. So when we plug in our amp, which I have represented here as our DUT or device under test, as I said before, some of this hot signal is actually going to leak onto the chassis. Well, connecting a hot signal back to earth ground is going to cause a dead short right here, and with no load, we'll see some sparks fly.
So let's look at this diagram here and see how the isolation transformer here helps protect us against this. So the job of this isolation transformer is basically to break this connection to ground here. And how it does that is we have this one-to-one transformer, so it has the same number of windings on each side. But as you can see, this loop here has no connection to ground. So since this loop here is not connected to earth ground, we can actually touch either one of these ends here individually and not get a shock. So similarly, this BNC connector connected to the chassis here is not going to complete this circuit here. So it's not part of the same loop, so we won't get any shock. So that's basically what the isolation transformer does. It avoids any potential shorts to dead shorts to ground. Let's quickly demonstrate this. So I have the amp plugged in directly to the wall outlet and the amp is turned on. If we turn our multimeter to AC voltage and place one end on the chassis and the other end on the BNC connector, which is connected to earth ground, we see a potential difference of almost 29 volts AC. Now if we connect the amp through this isolation transformer here, we're still going to get some AC voltage on the chassis, but we can safely tie our oscilloscope ground probe to the chassis since the earth ground is no longer part of the power circuit loop. And the other way we could have solved this is to install a 3-prong power cable and connect the ground wire to the chassis. And I might end up doing that in the end, but for now we'll just use the isolation transformer. All right, so we're almost ready to inject our signal, and if you recall, we're going to skip the phono section here and plug into the auxiliary amp here, which is going to feed through these resistors here, and then it's going to feed up through pin 1 up into our grid of the 6AU6. And if we look at our little testing chart that they provided, we want to see 0.025 volts, which is 25 millivolts on the grid, and we expect to see about 2 volts on pin 5, which is the plate. Just reading a section from the manual that I found online, and I can actually see that the auxiliary amp input is actually an output. So we can see here that the model 532 amplifier is provided with an auxiliary amplifier output socket, which is not governed by the phonograph volume control, but does have the advantage of automatic level control. So even though this was designed as an output jack for the signal that's actually coming out of our preamp section here, I still think it's safe for me to use as an input into my power section of the amp over here. But just to be safe, I'm going to remove the tubes in this preamp section, the 12AU7, the 12AX7, and the 6AN8. And that's just going to eliminate any interference or possible negative feedback that could come from the preamp section of the circuit. So for testing, I'm going to leave my 6L6G tubes in, as well as the 12AX7 and the 6AU6, but I'm going to remove the 3 other tubes when we do our testing. I have my signal generator ready to go here. I have it set to 1 kilohertz at 25 millivolts peak to peak. I just have a BNC cable here that's has a BNC to RCA. I just hooked up my scope probe to that just to make sure that I'm getting a nice clean signal at 1 kilohertz. So that's looking good so far. So I turned my signal off, but as mentioned in our test strategy, we're going to be plugging the RCA signal into the auxiliary amp input. So when we inject the signal, we're going to put the oscilloscope on a couple points here. We're going to put it on the input to the grid here, which is pin 1. So we're going to tie our one scope probe to C16. And the other one, we want to see the output on pin 5, but we're going to do it right after the coupling capacitor to make sure that we avoid any high voltage DC. So we'll plug it on to C20. So we have a printout of the circuit board here, and C16 is this capacitor right there. So we're going to put one probe here, and C20 is this one here. So we'll put the other probe on C20. So here's where I have my probes connected. I'm just going to turn the amp on, let it warm up for a few minutes before we apply the signal. Okay, so the tubes have been warmed up. I'm just going to output my signal. And look at that. We are getting a nice clean output signal. It's getting amplified. It's out of phase as we expected. And we have about 20 millivolts coming in peak to peak, and we are expecting 25. It's a little less. That's probably okay. Oh, on this secondary wave, we're only seeing about 800 millivolts peak to peak. So If you recall from our signaling chart, I was expecting about 2 volts on the output. So we're only getting about half of what we expected. So I think we're going to actually have to look into this. We're not getting the amplification that I was expecting to see. So the first thing I'm going to check is my plate voltage. I want to make sure I'm seeing about between 1 and 200 volts on my plate there, because that's what this tube is designed for, according to the spec sheet. So I'm going to measure the DC voltage on R34 here, and make sure that I'm getting the proper DC voltage in. So R34 is this resistor next to the 6AU6 here. All right, I have my multimeter set to DC voltage. I have one probe connected to the chassis. In the other one, I'm only seeing 37 volts DC. That is very low. So we'll have to see why we're not getting our proper B+ voltage there. So I just pulled up the specs for the 6AU6, and like I suspected, we should be seeing about 250 volts DC at the plate, whether we're in pentode or triode mode. So we're not seeing that, so we'll have to investigate why we're getting 40 and not 250. Okay, let's see where our plate voltage is coming from. We start with the 5U4G rectifier tube here. We're going to come down through this line here. It's going to be center tapped. And then we come down through R69A, so we have a voltage drop here. And then that voltage drop is tied into this line here through R63 and R34. So we really have 3 resistors that we have to check and make sure that we're not getting any excessive voltage drops. Okay, so we have our chassis turned over, and let's just follow this along here. We have pin 8 of our rectifier tube, and it's center tapped, but it's also coming through this resistor here, which is R69A. That's coming along to our power tubes, which is pin 4 here, which is also connected to this power tube through this orange wire. So then we have another orange wire that's coming out from that point, and it's running over to our resistor bank here. So that will be our next resistor that we're going to pass through, and that's R63. So one of these will be R63, so we'll check that point. It's actually this one here, because I can see the pink wire runs up, and that will connect to our circuit board, which will go into the next resistor, which is R34. So let's check the values of those resistors. So this one is 1.5K, and that is R69A, and it is supposed to be 1650 ohms, so it's less than the spec, so shouldn't be a problem causing an excessive voltage drop. Next one is R63, and for that one we are getting, I'll probably have to remove this from circuit to actually get a valid reading, but right now it's looking like it's about 13 kilo ohms. And according to the specs, we should only be getting 12K. So I might actually have to replace that resistor. 10% tolerance is okay, but we're pretty high for that one. All right, so let's check the voltage drops across these resistors. So I have my multimeter set to DC voltage, and coming off my rectifier tube, I am seeing about 470, 460 volts here. And then across on the other side, we're dropping that down to 407 through this resistor here. And then we come into my 63 here, which is still 407. And then we drop it to about 350 volts after 356 volts after R63. Okay, so I have the amp off and disconnected my tubes because I want to test the resistance of R34. And it is supposed to be 120K, and we're seeing, again, a little bit higher than I expected, about 125 kilo ohms. Okay, so I plugged my 6AU6 tube back in, turned the amplifier on, and we'll measure across R34. So we're getting 356 volts in, which is what we saw from on the other side there. And on the other side, we have a voltage drop to 43 volts. That's no good. We need to see at least 75 to 100 there, so getting about half. So I suspect we have probably a bad resistor here. I think I'm going to have to replace some of these. So on the schematic that I have, on the other side over to the right here, we actually have another chart that looks like provides the expected DC voltages. And if we look at our 6AU6, we see that on pin 5 we should be seeing 73 volts, and we're only seeing 37 or 40. So there we go. So we're only seeing half the voltage on for our B+. So I think we're going to have to replace some of these resistors, and we'll try it again. It's probably also good to check the voltages around the tube as well. So we want to see about 0 volts on the grid here. So we'll check C16 to make sure we got 0 volts on that pin. And we'll check the cathode here. So on R31, we want to see about 1 to 3 volts DC. And on the screen grid here, on C18, we want to see somewhere between 50 and 150 maybe volts on the screen. So we'll check those voltages as well. So those test points on our circuit board, C16, that's our grid. We want to see 0 volts there. We have R33, which is our screen. We want to see somewhere between 50 and 150. And we have R31 way up here, which is our cathode, and we want to see between 1 and 3 volts on that one. Okay, so C16, we are seeing 0 volts DC. That looks good. R33, we are seeing 130 volts. So that's between 50 and 150. That's what I expected to see. That looks good. And then R31, we are seeing 2.6 volts. That is our cathode resistor there. So that looks good as well. So since the other voltages around the 6AU6 tube are looking okay, I think that the tube is biased properly. So let's just go ahead and remove R34 here and replace it with a new resistor and see if that resolves the issue. So on our printed circuit board, R34 is this resistor right there. Okay, so I've gone ahead and discharged my capacitors as shown in the first video, part 1. And the next thing I'm going to do is use a solder wick and wick up as much of the solder. We can see that our line is coming in actually from there, that pink wire, and our resistor is going right across to here, which goes into the 6AU6 tube here. So I'm just going to add a little bit of flux on these points right there. And then I'm going to use my soldering iron with a solder wick to soak up as much of the solder as possible. The goal here is to remove the component without wrecking any of the trace. So the best way I've found to do that is to use a solder wick to soak up as much solder as I can so I don't wreck any of the trace that's on the board. So with our solder wick, we're just going to soak up as much of that solder as we can so that we can actually pull the resistor through without damaging any of the trace. There we go. It's pretty clean now. I'm just going to use some tweezers and straighten out the pins so that we can pull it nice and straight through the other end there. Finally, I'm just going to use my tweezers here and pull that resistor out. There we go. Okay, we have that resistor removed. I'm just going to measure it out of circuit. We're getting 127 kilo ohms, so not terrible, but definitely higher than the spec of 120 that's called for. Okay, so I'm going to be replacing that with a 120 kilowatt resistor with a 1 watt power rating and 1% tolerance. The spec only calls for a half watt with 5% tolerance, but having a higher power rating is completely fine. It just means it can handle a little bit more power. Since I was right next door here to the grid resistor, I decided just to replace it as well. I was getting 157 kilo ohms on the measurement, and it's rated for 150K, so figured if I'm there anyway, I might as well just replace them both. Alright, so I have those two resistors in place. I'm just going to add a little bit of flux again to the ends here, and we'll get those soldered in. Okay, so once those are soldered in place, I'm just going to use a little bit of rubbing alcohol and a Q-tip and just clean up any of the flux residue that was left on the board. The flux residue is highly acidic and it'll eat the board away. Sometimes it's conductive as well, so we just want to make sure that we clean that up as best as possible with some rubbing alcohol and a Q-tip. Okay, so we have our resistor replaced and have our amp turned on, and we are now getting 62 volts, which is a definite improvement. Alright, so we ended up replacing the plate resistor 34 as well as the grid resistor 33 here, and we definitely saw an improvement.
So what that tells me is that we probably have 31 and 32 that are also quite high, which is increasing the voltage too much on the cathode side. So I think what we're going to do next is replace 31 and 32, and we'll see if that gets the plate voltage in the correct range. So on the circuit board, that's these two resistors here, 31 and 32. We'll just use the same process to remove them and replace. So we have R31 pulled out here, and it is 680 ohms, and we are getting 740. So again, is much higher than we expected. And R32 is rated at 330K, and we are getting almost 400K. So again, way higher than expected. So we replaced our screen and cathode and plate resistors for the 6AU6, and we'll measure the voltage. And we're still only reading about 60 volts on the plate.
Okay, so we replaced most of the resistors on the 6AU6 here. So the next thing we're going to try is this other resistor, which is R63. That's coming in from our transformer.
So R63 is supposed to be a 12K resistor, and we are reading 13K, so once again on the high side. Okay, so we've replaced R63, and we are now getting 65 volts at the plate. So that's definitely an improvement and closer to the 73 volts that we see on the test chart.
I've come to the realization that there's probably not much point in continuing the signal tracing through the circuit, as every single one of the carbon barrel resistors here that I've tested has drifted higher. And so I think we're going to have to actually replace them all with the metal film resistors before continuing. Carbon barrel resistors have a lifespan between 10 and 50 years. We're probably at that age right now with this amp. Our board has been recapped, but it's probably time to replace the resistors. So I'm just going to replace them all with metal film resistors with the same method I used before, and we'll check back in when it's done. Okay, so I've gone ahead and replaced all of the carbon barrel resistors on the back half of the circuit here, including the ones that are on the underside of the chassis that were on the back half, like these ones here. So these have all been replaced, and what I'm going to do next is just inject that signal again and make sure we're getting a nice clean amplified signal all the way through to the end before we proceed with the phono section. As you can see, I've replaced all of the back half of the circuit with some new metal film resistors, and we still have the old carbon barrel resistors on the phono preamp section. Alright, so I have one probe again connected to C16, which is the grid, and the other one connected after the coupling capacitor on C20. After a bit of reading, I also found out that these voltages here are usually implied to be RMS voltages and not peak-to-peak voltages. So in my next test, I'm going to use 25 millivolts RMS. Okay, so the tubes have been warmed up, and I am now applying a 70 millivolt RMS signal on my line there. And I am getting a nice, perfect 25 millivolts peak or RMS on the input signal, and almost exactly 2 volts, which is what I expected to see on the plate side. So that's looking pretty good. So we did their probe testing on the grid and output of the 6AU6. Now I'm going to move over to my phase inverter tube here, and I'm going to put the oscilloscope probes on the outside of C27 just after these coupling capacitors and C29. On the circuit board, that will be at these 2 points right here. Alright, I have my 2 oscilloscope probes hooked up to those 2 coupling capacitors. I'm just going to apply the signal, and we are getting a very nice clean signal. It looks like they're off just a hair. If we look at the bottom here, we have 7.6 volts RMS on the one, and 8.2 RMS on the other side. So I think I can explain that. Let's go back to the circuit and take a look here. I forgot to mention that there was one resistor value that I did not have on my shelf, and that's on order right now, and that was the 510K resistor R74 right there in the middle of the screen. And that is the resistor right there, R74, that is coming to the plate of my second half of the 12AX7. So I have a feeling that once again, all of the resistors that I pulled off so far have drifted higher. I have a feeling that that resistor is just too high, and once I get the replacement, that my signals will be perfectly matched. All right, so next I want to test the output signal from these power tubes here, which is pin 3 on these two tubes. However, because they have such high DC voltage on those pins, for safety reasons, what I'm going to do is just go straight to the output side and test pin 6 and ground here. And if that has a good signal, then we can assume that we have no problems with the output on the 6L6G tubes. All right, so I have my purple probe hooked up to my dummy load here, and we will apply the signal and see what happens. Okay, so we are ready to apply our signal, and look at that, we are getting 7.86 volts RMS on the output. That is looking really nice, really clean, no signal distortion. I think the back half of our circuit is looking really good. Just for kicks, I want to hear what the amp sounds like, so I'm going to replace my dummy load with an 8 ohm speaker. So we have that hooked up. I have one probe attached to it, and I'm going to use my iPod here through the headphone jack to apply a signal to the auxiliary jack. Here comes the sun, here comes the sun, I say it's alright. Little darling, it's been a long, cold, lonely winter. Little darling. So in part 1 of the video, we focused on the power supply section there of how to test that. And in part 2 here, we've successfully applied a signal to our auxiliary amp here, which was actually an output, but we used it as an input. We just disconnected all these tubes here and tested our signal all the way through the voltage amplification of the 6AU6, the 12AX7 phase inversion, which comes down through our power tubes, out through to our power transformer here, and the speakers. So part 2 of this video is getting quite long now. I think this is a good point to take a break, and maybe we'll do a part 3 that focuses on the phono preamp section of the board here. I'm going to go ahead and probably replace all of the carbon barrel resistors that I'd had to do on the back half, since all of them had drifted upward quite a bit, so I expect the same problem will exist on the front half. So I'm going to do that in part 3 of the video and explain how the phono section works in part 3. I hope you guys enjoyed this part and look forward to seeing you in the next part.